get started. So I'm Dan Westervelt. I think most of you know me, but so I'm mostly working out at Lamont as an associate research scientist, and then I also work a little bit here at GISS on one of the microphysics models, TOMOS. But I'm not going to talk much about the TOMOS stuff today. I'm going to talk about my research on connecting regional aerosol emission reductions to local and remote temperature and precipitation responses. So this is a collaboration between GFDL, GISS here, of course, and NCAR. And so our funding is from NSF. So just a little bit of background, although I think everyone here is going to know all this stuff. So aerosols emitted directly from sources and also produced indirectly from precursor gases from all kinds of different sources: wildfires, fossil fuel burning, desert dust, biofuel, biomass burning. This is just a plot of aerosol optical depth showing kind of different hotspots associated with different sources of aerosol emissions. And of course, these aerosols impact climate in a variety of complex ways. One of the main ways is through the direct effects of aerosols, which is just the interaction of incoming solar radiation. So this can be scattering and absorption. Different species may be better at doing different types of extinction, whether it's scattering or absorption. And then there's also the indirect effects, which are, in short, kind of a modulation of cloud properties. Here I have a schematic showing somewhat of at least the first indirect effect. You have sort of a clean air mass with lower aerosol pollution on the left and a hypothetically more polluted air mass on the right with more aerosol pollution. The more polluted one is going to have more aerosols, of course, and therefore more cloud droplets. It's going to have a higher cloud droplet number concentration. And so for an equal amount of water vapor, that's going to be spread around more thinly in the sort of polluted hypothetical environment, and you're going to have therefore smaller cloud droplet size. This smaller cloud droplet size leads to a higher surface area of the cloud and therefore a higher albedo of the cloud. So basically the brightness of the cloud is increased. So when incoming solar radiation comes in, less of it sort of gets through the cloud, more of it is reflected back. This is called the cloud brightness effect, or the first indirect effect, and it exerts mostly a cooling influence on the climate, as you can imagine, with more solar radiation being bounced back to space. There's also another indirect effect, at least one more for that matter, involving precipitation. And so for aerosols and precipitation, there's a really complex view here. But to show first the microphysical view, first of all, again, I have this same set of sort of schematic with the top row being the cleaner atmosphere or a cleaner air mass, and the bottom row being the more polluted one. The first two panels here are just showing the albedo effect again. But then the other indirect effect is more of a cloud lifetime effect. And so in this scenario, the same kind of mechanism, those smaller cloud droplets that are associated with more aerosol pollution may be less likely to rain out. I say may because there's a lot of complexity there. And in that case, if they're less likely to rain out, they may extend the cloud's lifetime longer and increase the cloud water in the atmosphere, the cloud liquid water path, and therefore cause more reflection of solar radiation and another kind of compounding cooling effect on the climate. So
does that depend where the clouds are?
Yeah, it depends where the clouds are. I mean, yeah, ice clouds may have different effects on clouds. I'm mostly talking here about warm liquid clouds in sort of mid-latitudes, maybe over the ocean or something like that. So basically, summarizing those processes I just mentioned, there's a decrease in the autoconversion rate, which is kind of the translation of the cloud droplet to the rain, which delays precipitation and there increases cloud liquid water. All of these things are attributed to sort of decreasing precipitation with increasing aerosols. But there's also some possible frameworks and mechanisms that have been put forward that say exactly the opposite, that increasing aerosols might result in increasing precipitation. And so one of those has to do with enhanced entrainment of dry air. So this was put forward by Andy Ackerman, who's not here right now, but this is kind of one of his main research topics where he kind of saw that there's actually more of a competition between this more liquid water in the cloud that's coming from the suppressed precipitation, but there's also a competition between that and drier air aloft. And so in some cases they found that the entrainment of drier air aloft actually dominates the effect of aerosols, and it causes a reduction in cloud liquid water path, and it has sort of an opposite effect from what I'm showing here. So the point is that these aerosol effects aren't quite fully figured out yet. These are still pretty uncertain, and I just wanted to give you a flavor for how why that is and what are the other kind of thoughts that are out there. There's also this idea that aerosols may invigorate deep convection and therefore cause increasing precipitation. And so basically these aerosols that don't necessarily rain out right away may survive longer up into higher parts of the atmosphere where they may ice nucleate or cause further rainfall in sort of a different regime. And that would be another case of how increasing aerosols may increase precipitation. So the cloud, I think the albedo effect is a little more understood, but the cloud lifetime effect is still pretty not well understood. So there's also more of a large-scale dynamic view that you can take with the aerosol effects on precipitation. I mean, this is sort of just a consequence of the direct effect. But aerosol extinction, whether it's scattering or absorption, can result, or does result, in reduced surface solar radiation. So less solar radiation reaches the surface. This is going to cause, of course, the land to be cooler, but also cause a reduction in convection. There's going to be less convection, so there's going to be less updrafts and less overturning circulation. And there's also going to be reduced evaporation because of that lower heat. And so that's another major way that aerosols can affect precipitation, is through their impacts on large-scale circulation. And an example of where this comes up with is in sort of the monsoon regions in India. And this figure here is from Deepti Singh from a few years ago, showing kind of just the schematic of, here you have these aerosols scattering or absorbing light, less gets through to the surface, you cause kind of a weaker circulation, which reduces your rainfall.
Pretty strong there with that, though, right? Because you could have absorbing aerosols that actually increase evaporation just by increasing the, increasing the volume, offsetting the volume cooling.
Right, so yeah, this is sort of a simplistic picture looking at maybe like the net effect of aerosols. I mean, yeah, in certain cases, right, I mean, you involve black carbon or dust or something, some absorbing species, then yeah, like this whole explanation is sort of turned on its head, but yeah. Which is kind of a good segue to show this figure from AR5, direct radiative forcing from aerosols and indirect radiative forcing. So black carbon, of course, a warming agent. It's this bar right here. The other aerosol species mostly show up as cooling, so a negative radiative forcing. And then the cloud effect here, you can see is also thought to be negative, has a very wide uncertainty range, just like, even wider, I guess, than the direct effect. But going with the sort of net effect, we would say that there's probably a cooling effect of the aerosols on the climate. There is some dependence on composition, black carbon, of course. And the aerosol cloud interactions and the aerosol precip interactions are very uncertain still. There's also a major reason to reduce our aerosol concentrations in the atmosphere, and that is because of the effects of particulate matter on human health. So in 2015, about 4 million people died prematurely from global ambient PM2.5. This is a plot of time versus deaths attributable to PM2.5 going back from 1990. This is from a groundbreaking paper in The Lancet. So you can see there's been kind of a steady increase. It's broken down by the different types of ailments that cause the premature mortality, but it does seem to be rising. Most of these effects are happening in India right now, China, Africa as well is starting to have a big problem with air pollution. But the point I'm trying to make here is that aerosols are going to need to be reduced for this reason. And so that's going to have kind of an impact on climate, and that's still pretty much uncertain. And models and observations are now showing that aerosols and their precursors are decreasing. So this is from a recent paper looking at global SO2 and black carbon emissions in the historical 1960 through the future scenarios, through 2100. So at the top you have SO2 emissions, the bottom you have black carbon. The gray shading that you can sort of barely see, I guess it's more of like a brown, is the RCP range for the future. And so the RCPs were all kind of reducing their SO2 through 2100 in this very sort of narrow range here. I don't know if you can see it, but it's pretty narrow what the possible different RCPs were. Same thing with black carbon. But looking at these new future scenarios coming out with AR6, the SSPs, we see kind of the same thing. I mean, there's going to be a decrease globally, but there is now a bigger range. So SSP3, weak air pollution control, you can see up here, has not quite the strong reductions that some of these other scenarios have in terms of their future pathways. And the same thing for black carbon as well. So we're expecting that aerosols are going to decrease. We've seen it in the observations already in a lot of places, which is what I'm showing here. So satellite retrievals from OMI are showing now that SO2 emission decreases are occurring in pretty much all world regions, including China. And so we've known for a while that SO2 emissions peaked in the US decades ago. But it seems like in China now we have some evidence of SO2 reductions. This is SO2 emission over time. Red is China. You can see there is kind of this slow, but over the last couple of decades, kind of a rapid decrease in the SO2 emissions.
This is an inversion of the local concentration?
Yeah, so there's some shortcomings with the method here. This is kind of a top-down approach, yeah. On the other hand, India is slowly still increasing its SO2 emissions, it seems like, using the same method. So not all world regions are decreasing, but most of them are, and we need to sort of know kind of what that impact has on climate. So kind of the main question that I'll be looking at is, what is the impact of both global and regional emissions reductions on future temperature and precipitation? And are these responses robust across multiple models? So with, in the era of CMIP and all of these, we have kind of a framework to use multiple models and assess robustness, and so that's something that I'd like to do. And then also, can we identify any of the underlying mechanisms, especially for the precipitation response? Can we sort of understand why aerosols might be affecting precipitation a certain way? Those are kind of my key questions. So first, looking at the global picture, this is some research I did several years ago now, but here I'm looking at sort of the end of 21st century climate response to global aerosol emission reductions in the RCPs. So this is if you follow RCP 8.5 in the future with its aerosol reductions, how much does that aerosol reduction in RCP 8.5 affect climate alone? And so what we did is we have a counterfactual simulation in which the RCP 8.5 scenario is entirely the same, except all anthropogenic emissions of aerosols are kept at 2005 levels. And then run that multiple ensembles transient simulations for present day at 2100. Compare that to just a regular RC 8.5 scenario where aerosol emissions are declining as they are projected to. All other forcings are exactly the same, greenhouse gases, land, all that stuff. So what you're doing by this is really isolating the anthropogenic aerosol effect. Oh, and I should say, and biomass burning as well. So when you do that, you can just basically difference those two scenarios. First, just to show you kind of the different RCPs in the effective radiative forcing due to aerosols. So historical, you have buildup of aerosol emissions, you have sort of this peak in aerosol direct and indirect forcing close to present day, and then as aerosols are slowly drawn down, you get a rebound effect in the direct and indirect radiative forcing over time. The different colors there are the different RCPs. But looking at kind of how the temperature and the precipitation change at the end of the century, you can see here that by 2100 or so, there's going to be an increase in temperature almost everywhere just from reducing aerosols. The biggest effect happens in the Arctic, but it's really kind of spread out over the globe everywhere. Precipitation down here on the bottom left. So this is what precipitation will do with respect to aerosol reductions by 2100. I should also mention this is only using the GFDL model right here. So this is just one model. There will be multi-model aspects later in this talk. But for precipitation, you see we have kind of a pretty big increase over the tropics, which kind of to be expected. Maybe some slight hinting of an ITCZ shift going on in the Pacific there. Some increases over the continents as well, over China and specifically South China, parts of North America as well. But you sort of get kind of, interestingly, you get this increase in most of the northern hemisphere and more of a decrease or no change at all in the southern hemisphere. And of course, the northern hemisphere is where most of these aerosol emissions are currently being emitted and therefore will be drawn down in the future. But kind of the take home of this is that there could be warming of up to 1 degree Celsius due to aerosol emission reductions alone by 2100. This is just with one model, but there's been studies since then and past studies that have found similar numbers, anywhere from 0.5 degrees Celsius to 1 degree Celsius in different models just from these aerosol reductions by 2020. So this is kind of an unintended consequence of removing the air pollution impacts of human health. The next steps are, I did this just globally, the next steps are let's look at it regionally. And let's say, okay, since different regions are sort of changing at different speeds, what could be the impact on climate for that? And then, of course, I already mentioned physical mechanisms and robustness. So the framework that I use for this regional modeling, the regional analysis, it's still global modeling, is use 3 different chemistry climate models. These are essentially the chemistry climate models in their CMIP5 configuration, not much difference than that. These simulations were run a few years ago. But we use the GFDL CM3 model, the CESM1 model from NCAR, and the GISS E2 model here. So these are models that have fully interactive chemistry and emissions, which is one of the linchpins of kind of this work, is that we're using these detailed chemistry models as well as the fully coupled climate models. So these models all include the direct and indirect effect of aerosols. The one exception is that in the version that we ran with the GISS model, we did not include the cloud lifetime effect. So that comes up a little bit later, but there was no cloud lifetime effect in our GISS models. In the GISS simulations. And our main kind of strategy is to run long control simulations. So we run a control simulation of the year 2000 conditions for about 400 years in each of these models. And then we contrast that with a sort of perturbation simulation, which is exactly the same, except for the anthropogenic aerosols in a certain region are set to 0. Okay, so for example, the US SO2 emissions set to 0, run that perturbation for about 200 years to sort of get to the equilibrium climate response. So we want to make sure the models are equilibrated. We don't want to. We're looking at sort of transient responses in a different project, but I'm not going to talk about that today. But run these long simulations and contrast them with a control for a bunch of different aerosol types in different regions. And we also run some fixed SST type simulations to quantify the effective radiative forcing. So it ends up being quite a bit of a lot of simulations, a lot of computational time and data. There was a total of 34 of these perturbation simulations across all 3 models. So total, not each model ran 34, but total among the different models. And these are the different regions that we've tested and looked at. And so, for example, over the US, we zero out the SO2 emissions, we zero out the black carbon emissions, so all separately. These are all kind of separate things. Zero out the organic carbon emissions, and then zero out all of them together, so all the anthropogenic in the model together simultaneously. We do that for each of the different models in the US and over Europe as well, kind of the same framework. Over India, we do kind of some of the same ones, 0 SO2, 0 BC. And then over China, we've only done, so this figure is a little out of date, we've done SO2, but we've also done black carbon. And then over Africa and South America, I'm not going to talk about these results much, but we chose to do our perturbations on biomass burning emissions. So we zero out the biomass burning emissions from all the different species, so OC, BC, and SO2 for both Africa and South America. And in some cases, you'll notice that, so I have 80% reduced here. This was to sort of get a roughly equal overall change in emissions. So China emits more SO2 than we do currently. So we didn't want to, if we reduced all of theirs all the way, then it would be kind of a different number than just zeroing out SO2 over the US. So we kind of tweaked that a little bit to match roughly the same emissions over the different regions. Just a quick little bit of model evaluation, just because that's sort of necessary. So I'm showing here on the top the precipitation rate, zonally plotted, so latitude on the x-axis, in the GPCP observational product in black, and the different models in the different colors there, GFDL red, NCAR blue, and GISS green. So you can see that except for the double ITCZ problem, which is well known for coupled climate models anyway, it does pretty well. Its model biases are less than 5%, with the big caveat being that there's this huge bias, the double ITCZ region. So there's a black line, here's the different models. Also looking at how aerosols are doing in the models. So I've plotted MODIS and MISR in black and gray here. Again, zonally, the AOD in the visible range, and then the different colors for the models. First of all, the MODIS and MISR themselves disagree with one another a lot, so you can see that there's a lot of uncertainty even in the observations. So keep that in mind when you're kind of looking at this plot. The models do okay in sort of certain regions, so north of maybe 30 latitude, but we see large model biases, especially in sea salt emission regions. So right here, the GISS model has a lot more probably sea salt aerosol going on at minus 60 south than the observations are showing. And similarly, we see this is probably evidence of kind of dust emissions that aren't being modeled to as accurately as they could in the GFDL model and the NCAR model here, is sort of right around the equator, I guess, just slightly north of it as well. But the model high biases are somewhat explainable. So I mean, like I mentioned with the aerosol, the aerosol kind of modeling of dust and sea salt could be improved. Also, it's sort of a different time period here, just a little bit. So MODIS and MISR has mostly been a product in the last couple decades, so after 2000. So what I did is I took a 2001 to 2012 average. The model is simulating 2000 conditions, so there's a little bit of apples to oranges. There were big emission changes, well, I don't know about big, but there were emission changes between 2000 and 2012, especially in US, Europe, kind of Western countries. So that could play a role with what's going on in this difference.
There's a lot of spatial and homogeneity too in the satellite retrievals. So now, for example, there are almost no aerosol retrievals in the summertime over India just because of all the monsoon cloudiness.
Right.
You showed a map earlier of the AOD, and both MODIS and MISR are really lacking observations over bright desert regions.
Yeah.
I don't know if you used MODIS Deep Blue to fill that in, but the point is that they're missing a lot of observations in places with a lot of aerosols.
Yeah. So I forget which of the deep blue or dark target, or maybe there's like a combined product as well.
Well, dark target was the classic original one.
Yeah.
Deep blue is the one that went out with just using UV.
Yeah, you're right. I mean, I think there's definitely shortcomings with those. I mean, they don't agree with each other a lot as well, as I said. So I'm going to give kind of an overview of some of our climate response to aerosol emissions work regionally. So we have 3 papers published on this now. One that looked at precipitation responses to removal of U.S. sulfur dioxide, another that looked at temperature responses to U.S. sulfur dioxide. So these were just U.S. focused, and then a third one that's just recently come out that looks at more of all of the regions together and tries to synthesize kind of an overall message. So first to look at the global annual AOD response due to U.S. SO2 removal. So what I'm showing for all of these type of maps is going to be the perturbation minus the control. So that's what the response is. That's basically the removal of aerosols, the removal of SO2. And so obviously for AOD, that's going to be a decrease everywhere. You get decreases mostly over the US, as you would expect, since you're removing US SO2. Although in the GISS model and also in the GFDL model, there are kind of these widespread across the Atlantic into Europe changes as well, which are kind of interesting. There's a lot of diversity in the model in kind of the global means, for example. And some of that is just because vastly different model treatments of aerosols. For example, the mixing states can be different in each of these models, which has a big effect on the optical properties. The CESM model is using a microphysics model, MAM3, very simple modal, 3-mode microphysics model, whereas the other two didn't consider aerosol microphysics. Other kind of assumptions as well can sort of cause some discrepancies. Oh, by the way, the gray dots mean that it's statistically insignificant. So if there's no gray, then those are statistically significant results. So one thing that we found that was kind of interesting in the AOD realm was that dust AOD actually is affected by this removal of US SO2 in a statistically significant way. So what I'm showing here is just for 2 of the models right now, the CESM NCAR model and the GFDL CM3, showing the dust AOD only in response to that removal of SO2. And so especially in CESM, you get statistically significant changes in dust over parts of Africa, parts of the Middle East, northern China, basically some of the dustier regions, the middle of Australia as well. You get these interesting changes. And so there's significant decreases in all of the models. I didn't show GISS because it's even smaller than the other 2. But in particular in the CESM runs, the total AOD, the dust AOD change alone was 1/3 of the total AOD response. So that's kind of interesting. You remove SO2, you expect most of the AOD to be sulfate related, but you actually get 1/3 of that coming from this feedback on dust. The GFDL model also has a little bit of a dust feedback, only 3% of the total. Still pretty large, but not as large as the CESM simulation. GISS, pretty small, so less than 1% of the total. And so what we think is probably going on here is this is a feedback of the climate system on dust emissions. So dust emissions are sensitive to changes in meteorology and climate in each of these models. Things like wind speed, precipitation. I don't know if precipitation is part of the dust emissions in GISS. Is that, it is? Okay. So,
Well, soil wetness.
What's that?
Soil wetness.
Soil wetness, okay, yeah.
So my guess is probably, Susanna Bauer found something like this, I don't know, like about a decade ago, but for her, this heterogeneous chemistry. So the point is that you have more salt. As sulfates go up, you have more.
Would that be increases though?
Yeah, that's true. So,
No, I mean.
no, okay, actually, you're removing SO2, I'm
Yeah.
sorry, yeah, that goes the other way, okay.
Yeah, no, this is just to cool the North Atlantic and the rain bands that move north.
Right. So, precipitation increases over Africa, and then that produces dust. Is kind of what I was thinking. So moving on to the effective radiative forcing due to that US SO2. So going to focus in on the US SO2 for a few slides here. As you can expect, again, changes over the US mostly. The global means are pretty close for CESM, 0.16, and GFDL, 0.17. GISS model, about a factor of 3 lower effective radiative forcing. And this is mostly because we think it's mostly because the cloud lifetime effects are not included in this version. So cloud lifetime effects, especially in the GFDL model, we've found it to be pretty high. It contributes a lot to the overall radiative forcing. And so the GISS model not having that seems to lower its total effective radiative forcing from removal of SO2. And then finally, for this is for temperature anyway, is getting to the changes in global annual surface temperature due to US SO2 removal. Again, showing the effect of removing SO2, so the response is the perturbation minus the control. You see a lot of similarities, especially in the northern hemisphere in the models, but you also see quite a bit of differences. So considering we tried to do everything as similar as we could in the different models, it's a little surprising at how kind of how different, especially the GISS model is here to the other two. They all seem to agree on this impact of on the Arctic, which sort of makes sense, polar amplification. But again, the GISS model has sort of the smallest response, probably tied to the effective radiative forcing. What we can do is calculate kind of a sensitivity of the temperature response to the radiative forcings. And that's what I did for each of the 3 models here. So the GISS model has kind of the lowest radiative forcing, so it is the most sensitive to the changes in temperature are the most sensitive basically to that perturbation. The GFDL model is sort of in the middle, and finally the CESM model has sort of the weakest sensitivity to equilibrium sensitivity of temperature to radiative forcing. Just for SO2, and just for the US SO2 on top of that. So now moving on to...
Your forcing was defined, like this is the effective radiative forcing that you're using and such.
Yeah, so it's the fixed SST method, yeah. Okay. So we're just running like short simulations with, fixed SST and sea ice cover. So looking at precipitation now, so this is the US SO2 change in precipitation. The largest increases again kind of happen over the tropics. The NCAR model has kind of a huge change going on here that sort of resembles an ENSO-like response, which we'll get into later. Each of the models seem to project a small increase over parts of the Sahel, or just maybe a little bit south of the Sahel, kind of in the Atlantic ITCZ region. You can see that here. It's hard to see the colors in GISS, but it's a tiny bit is there. But overall, things are kind of noisy. We think we have sort of an ENSO-like response that I'll get into later. And again, there's a weaker response with the GISS model. Now moving away from the US SO2 and actually getting into another simulation. So Europe SO2, what happens when we remove that? Again, we see that NCAR model has sort of this dipole type of response going on in the tropics. We also see the Sahel effects again, or the Atlantic ITCZ effects, but then the one thing that's, I think, different about this is that we now see a lot of local impacts. What I mean by that is that aerosols are changing in Europe. The precipitation rates are also changing a little bit in Europe as well. So here, maybe you can't see it too well, but there's a little bit of red in there in all 3 of the different models. I'll zoom in a little bit later on another plot. And then finally, China. I'm not going to go through all of them because that would just be way too many. But the China SO2 simulations, again, NCAR seems to do a lot of the same thing. The GISS model also has some kind of possible ENSO-like response going on, which we'll show later. The effects of Chinese SO2 has kind of a large impact on local China precipitation, which is sort of to be expected. So I think I've already covered most of these points, so I'll just kind of go on. So looking at the global mean delta precipitation, which is shown here in this plot, from all of the different simulations we did and all the different models. So blue is NCAR, red is GFDL, green is GISS, and on the x-axis is the different types of perturbation aerosol simulations we did. And the y-axis, of course, is delta P, precipitation. You can see that the NCAR model has the highest response to all these different varieties of perturbations. At the most, on a global scale, it's maybe a 1% increase of the control. The GISS model, again, sort of, in some locations, it is close to in the GFDL model, and so the NCAR model kind of stands out on its own on a global scale. Yeah. But, I guess the main point is that almost every simulation, we at least get kind of the same sign in the global precipitation. So removing aerosols in all these different regions causes an increase in all but one of the different aerosol removal simulations. So I mentioned the Sahel a few slides ago. So the same kind of plot here, but zooming in and averaging over the Sahel, defined by these coordinates, and specifically over the wet season, or roughly the wet season, April to November, kind of expanding the wet season a little bit there. But the rainfall increases about 10% compared to the control in a lot of the different simulations that we did. So for example, Europe SO2 and then Europe, all three of the anthropogenic together, cause a pretty big increase in multiple models in precipitation. So removing aerosols from a remote location can have impacts on precipitation in far away regions, remote regions like the Sahel. The US is also kind of a big one. US SO2 impacts Sahel quite a bit. And we see most of this happens in NCAR and GFDL. And so these are statistically significant. There's rainfall increases in 26 out of 34 simulations that we ran. And we think we have sort of a explanation for this that I'll get into in a couple slides. But I wanted to show kind of specifically what's going on here with daily precipitation. So this is plots of daily mean modeled Sahel precipitation smoothed with, I think, 15-day running averages or something like that. Over the different models for GFDL, NCAR, and GISS, and then the black line is the GPCP. You can see that, so the solid lines are the control run precipitation over the Sahel, and the dashed lines are the perturbation. So you can already see, there's kind of an increase there going on. The bottom plot is if you just take that increase and plot that, or take that delta. And so you can see, especially for the NCAR model, there's a huge, this ends up being, about 10% or more of the total precipitation over the Sahel in a given year. In these months, yeah, which is almost, these months are when it pretty much only rains in that area, as you can see from the observations. But the GFDL model in red here and the NCAR model in blue are showing kind of some substantial changes that we find significant. And so the question is then, what is causing these changes? And so it's a pretty straightforward explanation. So as emissions in the northern hemisphere, for example, in the US, which is what this plot is showing, as those emissions decline, the northern hemisphere is going to warm more anomalously compared to the southern hemisphere, since that's where the emissions are. And you can see that in the NCAR and the GFDL models here. There's a lot of warming in the Arctic and basically north latitudes there. So this causes sort of an anomalous interhemispheric temperature gradient, which then of course causes an anomalous Hadley cell circulation and acts to shift the ITCZ upwards. So the idea of the ITCZ shift is nothing new. That's been done with greenhouse gases and aerosols as well. But we see that even for these relatively small regional aerosol perturbations. So that northern, that shift, or that interhemispheric temperature gradient, causes this increase in precipitation kind of right over this band in Africa in these two models. The seasons are a bit different. So as you can remember on the previous slide, the peak in the NCAR model was more in June, July, August, whereas the peak in the GFDL model was a little bit later. So now what we did was we took that idea of that northern minus southern hemisphere temperature gradient and applied that to all the different model simulations that we did. So these symbols are the different perturbations, whether it's US SO2 or India, BC or whatnot. And I plotted all of those delta temperatures versus this delta Sahel precipitation. And you can see that this is just for the GFDL model right now, but you can see you have this pretty nice linear relationship, this linear correlation, where when you have a higher interhemispheric temperature gradient, you have a higher increase or higher change. It can be a decrease as well in the Sahel precipitation. Likewise for NCAR, there's a little bit more scatter, but we still have kind of a moderate linear correlation that sort of falls in line with what I was seeing before. And then for for GISS, we don't. So in GISS, I didn't show on the previous slide the interhemispheric temperature change there because we don't really see much of one. And therefore, because we don't see much of an interhemispheric temperature change, we also don't get much of a Sahel precipitation change. So although it's not behaving kind of like we would want to, it's at least sort of self-consistent in that explanation, in that we don't have some kind of precipitation change that isn't being reflected in a change in temperature there. So I guess kind of the take-home point of this whole area is that, you know, removing of aerosol cooling especially in places like Europe and the US, which are kind of making up these points up here, brings additional rainfall to the Sahel.
Do you know what it would look like if you took the observations, say over like, you know, the 70s, 80s, and looked at like where would they fall on that plot? Obviously, it's not just U.S. reductions.
Yeah, that's a good question. Let's see. Yeah, I don't remember off the top of my head how much the Sahel precip changed in like the drought era from the 70s, 80s, but so I'm not entirely sure. But yeah, it's definitely a good thought. We didn't do any of those type of simulations. Something to consider. Okay, so moving on a little bit here to the how much time should I shoot for, by the way?
Usually 45 to an hour.
All right, so let's do like 10 more minutes or something. So we also looked at Mediterranean precip. So Mediterranean precip has been decreasing a little bit over the last half century or so, and there's still kind of a lot of possible explanations about why that's happening. And one thing that hasn't really been discussed much is aerosols, and so we decided we were in a position to look at that. So mostly it seems like these different aerosol perturbations cause an increase in Mediterranean precip over kind of their wetter season, October through March. And what we think is going on there, so here I'm plotting the response in sea level pressure over the winter period and the response in the winter precipitation for a simulation where Europe SO2 are zeroed out. So you get this kind of interesting north-south dipole in northern Europe, which sort of looks like the NAO. The real NAO, of course, is more west. It's not like really over Sweden and Norway, it's kind of over here. But whether or not it's the NAO, it has sort of this effect of weakening the prevailing westerlies. So these are the wind barbs. You can see they're kind of weakening these westerly winds, and therefore shifting the storm track southward. And that brings to the Mediterranean area, southern Europe, kind of an increase in precipitation. So we think that this is probably somewhat of a robust explanation. It doesn't happen in all of the models, so there's still a question of really how robust it is, I guess. But it sort of the internal mechanism sort of makes sense, you know, in the context of kind of an NAO response, because the NAO kind of does the same thing, where the westerlies can get weakened, storm track can get shifted south, and it can affect precipitation in the Mediterranean or southern Europe. I'll skip this in the interest of time. So one other thing we did with our simulations is we noticed that there were maybe some ENSO type of responses, and we were interested in, is there any way that the regional aerosol perturbations are affecting ENSO, and then that's therefore affecting precipitation? And so to investigate that, we use this kind of linear regression type of methodology that's been used a few times before. But we basically take this index that represents the Walker circulation, or the Southern Oscillation, of two kind of boxes of sea level pressure, take the difference of those and regress that onto the precipitation patterns that we see. So that basically is this slope, this RP ENSO, which is kind of the slope of this regression. Then, if we take that and do the same sort of Walker circulation index in the perturbation simulations and the control simulation and take a difference there, that's kind of like your delta ENSO effect. And so if you multiply that times that slope, you have a rough estimate of the delta precipitation due to ENSO. And so that's exactly what we did with our various simulations of aerosol perturbation. So again, showing the delta precipitation just due to ENSO this time, or how I've defined due to ENSO. You can see that there tends to be a shift towards the positive phase of ENSO, first of all, so towards El Nino. There's a lot of different teleconnections to various ENSO-related areas, like the Indian monsoon. You see some drying. So this is the NCAR model, US SO2. You see some drying over Indian monsoon region, also in the GISS model, well, not quite the Indian monsoon, but Southeast Asia. You see some effects in the Amazon, so maybe some teleconnections there. And of course you see the largest impact in kind of the tropical areas. So this top row is for US SO2, the bottom row is for China SO2. The changes are at most maybe 0.1 millimeters per day, which is only about 20% of the total precipitation response. So if you just look at delta P, delta precip, whether or not it's regressed with ENSO, you get maybe 0.5 or so. So it could be about 20%, which you know, is an appreciable amount that I think is worth thinking about. Let's see. I'll talk a little bit about extremes in the last few minutes here. I'm almost done. So one other thing is that we're going to look at the temperature extremes and the precipitation extremes and how aerosol removal affects those. So the same kind of framework, the delta plots here. I've plotted the TXX, which is the maximum of maximum daily temperatures. So if you have all of your high temperatures in a day, you pick out the maximum of that. That's TXX. And then TX90P is percentage of warm days above the 90th percentile. It's kind of percentage of warm days rather. In the GFTL model, the CESM model, I'm still processing. This part is sort of ongoing work, so I'm still processing the GISS the GISS results. This, of course, all requires daily data, so it tends to be a bit process intensive. But we get similar kind of responses to US SO2 in both of the models. You see kind of increases in extreme temperature in the eastern US, some things going on in the northern parts of Europe or Asia, and then sort of similar ideas in the TX90P metric for GFDL and CESM. So aerosols seem to be also affecting extreme precipitation, not just mean. And this is definitely a fresh off the grill type of plot here. So, but one of the things that we're trying to think about is there any functional relationship between the extreme and mean responses to different aerosol perturbations? And so that's kind of what I'm trying to explore here with these two figures. So what I've plotted is the linear correlation coefficient of the change in the extreme temperature response versus the change in the mean temperature response to that perturbation of US SO2. And so kind of as you expect, it's mostly a positive correlation. That's a good sign. There's kind of this classic idea of a mean shift of the distribution of temperatures, where you get more extreme temperatures with that mean shift. That seems to be going, that seems to be holding up to the case here. I also plotted kind of the slope. So this bottom panel is the slope of the delta T extreme versus the delta T mean in GFDL for the US SO2 simulation. And here you see in certain hotspots you have kind of a higher slope than a 1-to-1. So Eastern US, Central Africa, Indonesia, China, parts of India, you have basically almost a value of 2, or getting close to 2 up here, meaning that for every 1 Kelvin or 1 degree Celsius of mean temperature increase, there could be up to a 2 degrees extreme temperature increase, 2 degrees Celsius in several key locations. So I had a few more results of extremes that are not all that surprising. So maybe I'll just go to my summary. So to summarize, globally, there could be a possible increase in global mean surface temperature up to 1 degree Celsius by 2100 due to aerosol reductions from human health concerns, so reducing the air pollution health burden. So air pollution emission reductions policies in regions such as the US and Europe can have far-reaching impacts. So I showed that they can, if you reduce SO2 emissions over the US or Europe, you can increase rainfall in the Sahel by up to 10% in multiple models. So we think it's somewhat robust. This could have a lot of different policy implications. It's not necessarily all benefits, because there could be increases in extreme precipitation, which could cause sort of disbenefits. So I'm going to refrain from saying that I'm just going to say it's far-reaching impacts, I guess. Global precipitation rates in all the different regional perturbations are mostly increases. And we find that the precipitation responses project onto known modes of variability, like ENSO and possibly the NAO. And the ENSO component of precipitation could be fairly high as 20%. And then the extreme temperature response is probably larger than the mean response. And we're looking for ways that these can be functionally related. So I'll stop there. Thanks.